Hello, everyone. My name is Hannah Turner, and I'm the president of the Marshall University Astronomy Club, MUAC. I thank you all for joining us for our Fall 2024 virtual speaker series. Drawing inspiration from our sister organization, the Society of Physics Students, SPS, which utilizes their series to spread science knowledge to the public, MUAC has created this series with the intent of capturing a glimpse into the minds of astronomers from our surrounding communities. A fundamental goal of MUAC has been and always will be to encourage astronomy discussions among upcoming generations. When we provide a platform for such knowledge to flourish, we aid a sense of possibility to all children within our local communities. Becoming an astronaut, an astrophysicist, or even a leader of a university astronomy group doesn't seem so impossible. I speak for all leading MUAC members when I say that we are very proud of what we have accomplished with this club. With that being said, I would like to introduce MUAC advisor, Dr. Sean McBride.
Thank you, Hannah. As Hannah said, my name is Dr. Sean P. McBride. I'm an associate professor here in the Department of Mathematics and Physics. I first want to thank Hannah. She's done a fantastic job organizing this speaker series, from reaching out to the faculty members around the region to helping to organize the flyers and advertising. So she's done a stellar job with this speaker series. So a round of applause for Hannah. She's done a great job. The astronomy club here is tied to the mathematics and physics department through me as their advisor. The club is diverse in its members, so you don't have to be a physics major to join the club. Our department here is a vibrant community of scholars who are both passionate about exploring the fascinating intersection between mathematics and physics. We have programs here that range in mathematics, physics, statistics. Those are undergraduate programs. We have graduate programs in mathematics with a MA degree, physical applied sciences, a master's of science degree, and then a master of science in physics. We have over 20 faculty members in the mathematics department in that program, or the mathematics program, and we have 8 faculty members in the physics program. There is around 8,300 undergraduate students here and 2,400 graduate students, and about 550 students in professional programs such as the MD program and PharmD program. 86% of our faculty have terminal degrees in their field. That's just some information to give you an idea of the size of Marshall and type of institution that Marshall is and the programs that we offer in our Department of Mathematics and Physics. If you have any questions about Marshall, it doesn't matter if that's about astronomy, physics, mathematics, any question about Marshall, please shoot me an email. My email is mcbrides@marshall.edu. So that's my last name, McBrides @marshall.edu. And if I don't know the answer to your question, I will be happy to point you in the right direction to somebody that would. And of course, if you have an interest in what you hear tonight from our speaker, I'm sure that they would be happy to answer any questions that you have as well, if you don't want to ask any questions in the end during the question and answer session online. So I think with that, I will turn it over to Hannah, and she can properly introduce our speaker.
Thank you, Dr. McBride. So without further ado, it is my utmost pleasure to introduce our third speaker in this series, Dr. Scott Gaudi, who will be speaking to us this evening on how to find all the exoplanets. This talk will span 45 minutes approximately, followed by a 15-minute Q&A period for all of our listeners to send questions within the live chat. We ask that everyone hold their questions until the end. Dr. Gaudi?
Thank you. Thank you for the introduction, and thank you for the invitation. I somehow have managed to switch my screen. Okay. All right. So welcome, everyone. I'm going to be talking about finding exoplanets with the Nancy Grace Roman Space Telescope. The image in the background here that you see is basically an artist rendition of what the Nancy Grace Roman Space Telescope should look like. I'll have more to say about what the Nancy Grace Roman Space Telescope is here in a second. I am at Ohio State University usually, although right now I'm on sabbatical and I'm at Goddard Space Flight Center in the suburbs of Washington, D.C. And so a lot of the work that I do is done in collaboration with NASA, and I work with a large team of people to try to facilitate the science, which I'm going to talk about today. Okay, so let's get into it. Sorry. What's happening here? I'm having trouble advancing my slides. Never had this happen before. Let me see if I can. Okay, here we go. Okay, so sorry about that. Does everyone see the next slide?
Yes, we can see it.
Okay, so one of the goals of studying exoplanets is to understand how planets form. We think planets form from in a sort of bottom-up scenario, and they start with small things and build up big things. And we think that planets form in a protoplanetary disk. So that's a disk of material that is surrounding a young star right after it's born. And in that disk, you have sort of dust grains, which are roughly the size of a micron or 1/1,000,000th of a meter. And those dust grains have to grow by 13 or 14 orders of magnitude in size and 38 to 41 orders of magnitude in mass to become the Earth mass and Earth radius and Jupiter mass and Jupiter radius planets that we see in our solar system and around other stars. So that is hard because as you traverse all of these different scales in mass and size, the physics that governs the accumulation of these planets into larger and larger bodies changes and can be quite complicated. So that is a big challenge in understanding planet formation. Nevertheless, up until 1995, we only knew of one planetary system. This is, of course, our own planetary system, although I've done a little revisionist history here and removed Pluto. But our planetary system, if you think about it, is a kind of an interesting system. We have four big glorified balls of rock sitting in the interior part of the planetary system. We have the most massive planet, Jupiter, which is composed mostly of hydrogen and helium, sitting right smack dab in the middle. And then as you go further out, the planets decrease in mass and size more or less monotonically and decrease in the amount of hydrogen and helium that they contain. And so, why does our solar system look like this? And given that we had hundreds of years to think about it, only one planetary system, we came up with a pretty good story for why our solar system looks the way it does. And the basic story, which I won't do full justice to, but it goes like this. So stars form from what we call molecular clouds. So molecular clouds are giant clouds of a million times the mass of the sun that are kind of floating throughout our galaxy. They're very cold. They're not very dense. But occasionally a part of that cloud will become a little bit denser and will actually become unstable under its own weight. So it'll start to collapse under its own weight. And when it does that, this very center, some of the material goes to the very center and forms a dense hot ball of gas, which eventually will start nuclear fusion and become a star. But some of the material ends up in a disk surrounding the star. As the protostar, that disk is conserving angular momentum. So it's a disk rotating around the star that's initially quite hot, but over time it cools off. And as it cools off, little dust grains, solid particles begin to condense out of the disk. They go from gaseous state to solid state. And exactly what kind of dust grains condense out of the disk depends on where you are. If you're very close to the star, it's very hot. So only things that have that evaporate at very high temperatures can live. As you go further out, things that evaporate at lower and lower temperatures can condense out of the disk, and those can form the building blocks of planets. And at some point, you reach a temperature where the disk is cold enough that you can actually have water ice. And water ice is very important because the two most abundant elements in the universe that like to combine with other elements are hydrogen and oxygen. And those are what obviously make up water. So the amount of solid material you have to form planets is much larger beyond this critical line, which we call the snow line, where you can actually have snow or ice in the protoplanetary disks. So interior to the planetary system, you have these big balls of rock. because that's the only material you have available to you. Exterior to the snow line, you form planets that are much more massive because you have more material, you form them much quicker, and they eventually get up to the mass where they can start grabbing onto hydrogen and helium. And since the hydrogen and helium is much more abundant than any other element, they form very large gas giant planets. That process takes longer as you go further out in the protoplanetary disk. So Uranus and Neptune are sort of failed gas giants. They never quite got massive enough, fast enough to accrete all that, to grab onto all that hydrogen and helium. So that matches our solar system quite well. So you have one data point. You better be able to come up with a theory that can explain that data point. And naturally, we thought this was such a compelling story. We thought that when we went to finally develop the technology, sort of in the late 80s, 1980s, that to find planets around other stars, that we would find solar systems that look like ours. Well, the truth turns out to be much more interesting. And in 1995, a planetary companion was found around basically a star very similar to the Sun, 51 Pegasi. But this planet has a mass of roughly 60% the mass of Jupiter, but it has a period around its star of only 4.2 days. So it's a giant planet like our own Jupiter, but rather than being in the cold outskirts of its planetary system, it's sitting right there, very close to its parent star, well within the orbit of Mercury in our solar system. So and we think this planet must have formed further out for the reasons that we think Jupiter lives where it is, but somehow it migrated in to the hot environments as it got older, kind of like retirees migrating to Florida. And so why is that? What caused that to happen? Why is that planetary system so different than ours? So we realized that planet formation was actually a lot harder than we thought it was. And we've since found many thousands of planets that have an amazing diversity of properties, most of which look absolutely unlike anything in our solar system. And so we've struggled to actually understand how planet formation works in these different systems. So how are we going to go about trying to solve this problem? How are we going to try to understand how planet formation works? So the hypothesis is that the physical processes at work during planet formation, the process by which you take the dust grains and grow them into larger things, and then ever larger things, and then how you grab onto hydrogen and helium, those physical processes of forming the planets, and then how those planets move around in the planetary systems after they form, should leave some sort of imprint or fingerprint on the distribution of planets that we see today, how those planets are distributed in terms of the mass of the planets and their separation from their host stars, in the same way that the distribution of planets in our solar system reflects something about the physics of what happened in planet formation. So the plan is, if we can measure these distribution functions, if we measure where planets live in terms of their masses and their periods and around what kind of stars, and we do that over a broader range of planet and host star properties as possible, then we can use these imprints of the physics of planet formation to understand how planets form. And we call this in the field measuring the demographics of exoplanets. So you can think of this as going out and sending out a census form to all the nearby stars and say, hey, tell us about the planets in your family. How massive are they? How far away are they? And we take that information and then try to use it to understand how planet formation works. The challenge is that planets are extremely small. In particular, they're extremely small in comparison to the stars that they orbit. So just as for reference, Jupiter is 1/10 the size of the Sun. It's 1,000th the mass, and it's about 1 billion times fainter. The Earth is about 100 times smaller, about 1/300,000 times less massive, and about 1 trillion times fainter. So planets are very small and very faint. But we have developed tools, and we developed the technologies, like I said, in the end of the last century, to enable us to detect these planets. And these are the tools we have available to us, and I'll go through each of these briefly. And I'm just going to mention the big 5, which are the main tools we have. There are other ways of finding planets, but they tend to be only applicable to certain kinds of planetary systems. Okay, so the first method is the method that was used to discover 51 Pegasi b. And here we just use the fact that planets don't actually orbit stars, they orbit the center of mass of the planet-star system. Similarly, the star orbits the center of mass of the planet-star system. So as the planet orbits the star, the star moves in a somewhat smaller orbit. And so, you know, you can imagine as the if you look up in the sky at stars, as those planets orbit those stars are moving in their little orbits. And if they're moving along our line of sight, then their velocities are changing. They're coming towards us. And then later on in the period, the star is going away from us. And when that happens, we actually can measure a Doppler shift. We can measure the change in the frequency of light coming from that planet caused by the fact that from the star caused by the fact that the star is coming towards us and away from us. The direct imaging method is in some sense the simplest method. Here, we're just trying to detect light from the planet itself. So this is an image showing a four-planet system that has been directly images, and each of those little dots of light surrounding the dark hole is a planet. The dark hole is because we blocked out the light from the star because it's so much fainter. Astrometry works very much like radio velocity, except instead of measuring the wobble along our line of sight, we're measuring the wobble on the sky. So the stars are wobbling, and we can detect those wobbles and infer the existence of planets. The transit method, which has been used to find the overwhelming majority of all known exoplanets, is also relatively simple to understand. If you have a planetary system and that system happens to be edge-on, so the orbit of the planet is located edge-on to your line of sight, every time the planet passes in front of its parent star, it'll block some light from that star, and we'll see the star get briefly dimmer. And by measuring those dimming events, we can infer the existence of the planet, measure its size. And then be it the final technique, all right. And so these methods have been used to discover the overwhelming majority of planetary systems. So this plot is showing all of the known planets at least as of when this plot was made a few years ago, all of the known planets as a function of their planet mass on the y-axis and their orbital period on the x-axis, and here the planet radius on the y-axis and orbital period on the x-axis. So, and the dots each dot is a planet, and the dots are color-coded by the discovery technique. So blue here is radial velocity, is transits, black is radial velocity. And then there's other methods. Well, these red are direct imaging. And you can see all sorts of interesting features in this diagram. You can see three different clumps of planets. These are the hot Jupiters that are similar to the 51 Pegasi b. These are Jupiter-sized planets located very close to their parent star. These are kind of super Earths or mini Neptunes, for which we have no analog in our solar system. Perhaps the most striking aspect of this plot is if you compare the known exoplanets to the planets in our solar system, there are almost no overlap. The planets in our solar system occupy a part of parameter space, of mass period space or mass radius space, that is very different than the most of the planets that we've discovered using our other techniques. And that's because those techniques are in general biased towards shorter period planets and more massive planets. So we really don't know how common solar systems like our own are, because we just don't have the sensitivity to those kinds of planets, at least not yet. So we're really there's not very many planets here, but it's not that we don't know that whether or not that's because there aren't any planets there or just we haven't been able to detect them. Now, you notice that there are some detections here in these kind of light blue or cyan colored points. Those are planets detected by a technique called microlensing, which I haven't had a chance to talk about yet. And that's going to be one of the main subjects of my talk. So most of the planets were discovered by the Kepler satellite. Kepler was sensitive to planets with periods less than roughly that of the Earth. So if you put this on a diagram of our solar system, this was the region of sensitivity of Kepler, which I'm sure you've heard lots about. Kepler was completely unable to detect any of the analogs to any of the planets like Jupiter, Saturn, Uranus, and Neptune in our solar system. So it's also the case that these other methods are really only sensitive to planets orbiting stars that are relatively close to the sun. So this image here is an image of another galaxy, which is probably very similar to our galaxy. If we could, zoom out of our galaxy and look down on it, it would look a lot like this. And each of one of these yellow dots and white dots is a planet that the star orbiting a planet with a planet orbiting it that we've discovered. And you can see that most of the stars live out here in the outskirts of the galaxy where the sun lives. Those are where most of the stars where we found planets around live. There are some that have this little spray out here. Those are planets discovered by the Kepler satellite. And then this spray is actually planets discovered by the microlensing method, which I'll talk about in a second. So really only the microlensing method is sensitive to planets that are actually quite far away. So we really don't know how common planets are in the majority of our galaxy. Okay, so the microlensing method is the fifth method at our disposal. It's probably the one you're least familiar with, but it has a lot of powerful properties, which make it very interesting and enable us to complete our accounting of planets using this method. The basic idea is relatively simple. So here you are, an observer. This is now shown as a telescope, and you're staring at a star in the sky. And if you stare at that star long enough, then another star will pass very close to your line of sight to that background star. So here's your background star that you're monitoring. Here's a foreground star that passes very close to your line of sight. When that happens, this foreground star will bend the light from the background star, splitting it into two images. Those images will be magnified by this foreground star. So the foreground star acts as a magnifying glass. So as it passes in front, the background star gets momentarily brighter and then fainter. And that the time scale for that to happen is roughly a month or so. The background star gets brighter and then fainter. Now, if this foreground star has a planet, and the planet happens to be located near the paths of one of these light rays, that planet will also bend the light and magnify it or demagnify it. And you'll get an extra little feature on top of your transient brightening. And that feature is what tells you that there's a planet there and tells you roughly the mass of the planet and how far it is from its parent star. Now, because these images pass in the region where our giant planets live around the parent star, we're most sensitive to planets in the outskirts of planetary systems, cool and cold planets. And that's very complementary to the other techniques where we're mostly sensitive to hot and warm planets. And in fact, microlensing can even detect planets that are not orbiting any star at all because those planets have mass, and that mass can bend the light from background stars and create these microlensing events in the same way that the star does by itself. So microlensing has a lot of very unique properties that make it very appealing to try to look for planets with. First, as I mentioned, it's sensitive to cool and cold planets, which are very complementary to the other techniques. It's sensitive to very low mass planets, all the way down to roughly the mass of the moon. Those kinds of planets are basically impossible to detect with almost any other method. They're sensitive to very long period planets, including planets like our own Uranus and Neptune. Sensitive to planets orbiting whatever happens to float along our line of sight to a more distant star. So that includes brown dwarfs. So brown dwarfs are failed stars, regular stars, and even stars, the remnants of stars after they die, white dwarfs, neutron stars, and black holes. We can look for planets around all of them with microlensing. As I mentioned, we can find planets that aren't orbiting any star at all, down to the mass of Mars. We can detect giant moons orbiting planets. We can detect multi-planet systems like our own. We can detect analogs of our own solar system. We can detect planets orbiting two stars rather than just one star, like Tatooine. We can detect planets that are in the habitable zone of their parent star, and we can detect planets all along our line of sight from here to the center of our galaxy. So we can really get a galactic census with this method. So how do we actually use this method to really complete this census of planets, to fill in that region of parameter space that's being missed by these other techniques? So we can write down what is required to do this. And I will just go through this very quickly. This is a little technical, I apologize, but just to give you a sense of what's required. The biggest challenge we have is that I said that if you stare at a star long enough, then a foreground star will pass in front of it and create a microlensing event. Well, long enough turns out to be about 500,000 years. And I don't know about you, but I'm not that patient. So instead of looking at one star for 500,000 years, we have to look at hundreds of millions of stars for like a year, and then we can detect thousands of microlensing events and hopefully detect many, many planets. So if we want to detect 100 Earth mass planets, we have to monitor hundreds of millions of stars. We have to monitor those continuously on the time scale of roughly 10 minutes, because that's how long the planet perturbs those images and creates that transient brightening or dimming. And we have to do that for about a year to get enough microlensing events. We have to measure those light curves relatively precisely. So that means we have to be able to measure their precisions to a few percent. Just for reference, Kepler was able to do this to a few parts per million. So this is a much easier thing to do than the Kepler satellite. And we have to look at regular stars in the center of our galaxy, and we have to be able to measure the light from the host star itself. So all of these requirements actually push us into space. And the reason for that is we have to look at a lot of stars. And in order to do that, we want to look at the center of our galaxy, where there's a lot of stars in the sky. But the center of our galaxy, there's a lot of dust between here and the center of our galaxy, which blocks a lot of that light. But that dust is more transparent in the longer wavelengths. So if we look in the near infrared, so those are wavelengths that are sort of twice what our eyes can see, up to maybe 3 or 4 times what our eyes can see. Those wavelengths are much more transparent to dust. So we can peer through the dust and then look and see a bunch of stars and then monitor those stars and try to find microlensing events. The problem is that the sky is really bright in the ground in the near infrared. But if we go above the atmosphere, the sky itself glows in the near infrared. But if we go above the atmosphere, then we no longer have that problem. We also really want to actually look at individual stars, but the atmosphere actually blurs out stars. So when you look up at the sky and you see the stars twinkling, that's because the turbulence in the atmosphere is causing that light to be bouncing around, and that smears out the light from the star. You can see that here. This is a simulated image of the center of our galaxy. Each one of these dots is an individual star. This is a blow up of that region. You can see lots and lots of stars here. And this is what that would look like if you monitored it from this ground. And so in particular, if you look, for example, here, you see something that looks like one star, but actually this is a bunch of stars all kind of glommed together because of the blurring effects of our atmosphere. So we want to be able to get images that look like this and not this. And again, that requires us to get up above the atmosphere. There's other benefits to space. For example, we don't have to worry about that pesky sun coming up. And so we can look at these fields continuously to make sure we don't miss any of these planetary deviations. And so all this enables us to do much more science and enables us to really harness the power of the microlensing method. So you can put this together and just write down, if you had the budget that you wanted and you could spend that money however you wanted, what would you have to build in order to really harvest all of the science you can get from microlensing to realize the potential of the microlensing method? And what you need is basically a space-based mission, as I argued. It's got to be pretty large, about 1 meter in size, in diameter. The mirror has to be about 1 meter in diameter. Has to work in the near infrared. It has to have a relatively large field of view so you can see lots of stars, so like a wide angle camera lens. And then you have to be able to look at the same fields repeatedly every 15 minutes. And you have to be able to do that for about a year. And if you write down all of these requirements, and then you ask, well, do we have any telescope that does this? The answer is no right now, but in a few years we will, and that telescope is the Roman Space Telescope. And this is not a coincidence. Roman was designed partially with this particular application in mind. It was designed to be exactly what we need to do this microlensing survey. So who is Roman? This is not the ancient Romans that we hear about in history. This is Nancy Grace Roman. So Nancy Grace Roman was the first chief astronomer at NASA. She was the first female NASA administrator. And she was also known as the mother of Hubble because she was instrumental in getting the Hubble Space Telescope up and launched. So she's very much an icon in the field, particularly in NASA, and we're very honored to have this mission named after her. Where did Roman come from? Well, there's a little bit of astropolitics here, but every 10 years, the U.S. astronomy community gets together and they appoint a panel of, with the world of the U.S. experts in astronomy, and it's a few people from other countries as well. And that panel kind of gets together and they get a lot of input from a bunch of people, and then they decide what we should be doing for the next 10 years in astronomy, and where agencies like NASA and NSF and the Department of Energy, where they should spend their astronomy dollars. And these decadal surveys are extremely influential. JWST came from a decadal survey. HST came from a decadal survey. Chandra came from a decadal survey. Spitzer came from a decadal survey. And the 2010 recommendation of the decadal survey for a large space mission was called WFIRST, the Wide Field Infrared Survey Telescope. And this was a mission that was based on several different mission concepts, which were submitted to the decadal survey. One was a cosmology mission to measure this elusive dark energy and dark matter and how it evolves over cosmic time. Another one was an exoplanet mission to do a microlensing survey, as I just mentioned. And the other one was to survey the entire sky in the near-infrared. And there was also the idea that you should be able to use this telescope for general observation. So that means that the community can propose for time to use this telescope to do their particular science that they're interested in, that is enabled by this telescope. So immediately after this recommendation, NASA put together a team of scientists called a Science Definition Team. I was a member of this team to kind of figure out if we could actually build this mission and what it would look like that would achieve these science goals. And we first came up with two different concepts, which were relatively small in size, 1.3 to 1.1 meters. Just as a reference, James Webb Space Telescope is 6.5 meters, HST is 2.4 meters. So these were really quite small telescopes in comparison to HST and JWST. They weren't super popular in the astronomy community. But then a very interesting thing happened. NASA announced that they had been gifted two space-qualified telescopes that had already been built by another government agency, which shall not be named. But if you want to know the name, you can look it up on Google. But this, just to give you a hint of what this agency was, NASA was told, or at least this is the story, that NASA was told that they could use these telescopes for anything they wanted, except they couldn't point them at the Earth. So these were two 2.4 meter space qualified telescopes, 2.4 meters, the same size as Hubble. And they had mirrors and spacecraft assemblies. So the idea was we could use these ready-built telescopes to save money and do a more capable mission. And well, at least one of those two things turned out to be true. And WFIRST was canceled 3 different times by the previous administration. It was brought back to life by Congress, and eventually it was renamed Roman, and other than a little hiccup during COVID, has been smooth sailing ever since. And I'll talk a little bit about the status of Roman here at the end of my talk. So what is Roman? There's a lot of words on this. I won't go through all of them, but the basic idea is it's a telescope roughly the size of Hubble. It has a field of view of 0.281 square degrees. I'll show you what that is compared to the full moon in a second. Operates in the near infrared, and the launch date is currently set for late 2026. It has a 5-year mission lifetime, which hopefully will be extended by at least another 5 years. And it's going to be located at a position called L2, the second Lagrange point. That's where JWST is. It's a very nice, quiet environment from which to do astronomy. And the thing that makes Roman very special is its very large camera. This camera is about 300 megapixels. and has a large field of view. So it's a wide angle camera lens that enables you to look at large areas of the sky at one time. Just to give you a sense of scale, so this is the actual detector, the camera on Roman projected onto a sky scene. And these are, for comparison, the sort of largest cameras that you have on HST and JWST. So you can see that this is much bigger, 100 times the area. This is the size of it in comparison to the full moon. So you can see that this is quite a bit larger, at least on this axis, than the full moon. And this is the nearest spiral galaxy to the Milky Way, Andromeda. So you can just point two pointings and cover most of Andromeda. This has been made possible by this 300 megapixel camera, which is extremely expensive, using very cutting edge technology in order to image this area of the sky in the near infrared. And this telescope not only has a larger field of view, but it's much more efficient than JWST and HST. So it's able to actually map the sky 1,000 times faster, which means you can map large areas of the sky relatively quickly, or smaller areas of the sky repeatedly in a reasonable amount of time. To give you a sense of scale of this detector, this is a simulated image of the center of our galaxy. And you can see that it's very crowded. There's lots of stars here. In this image, there are roughly about 1 million stars if you look all the way down to these very, very tiny dots. And this image is only 0.1% of the entire area that's going to be covered by Roman when it is looking for microlensing events. So there's going to be hundreds of millions of stars in that field of view. Just to give you another image, a blow up of this. And again, each one of these little dots that you can see is a star in the center of our galaxy that could serve as a source for microlensing events. Okay, so how many planets should we expect to see? So we don't know, because if we knew, we wouldn't have to do the survey. But we can make realistic estimates of how common planets are, and then we can try to estimate how many that the Romans should see. And that depends on a lot of things. It depends on how many microlensing events there are. It depends on what the field of view of Roman is. It depends on exact survey strategy, how often it looks at a particular part of the sky, how big of a piece of sky it looks at. So we can simulate all that and come up with an optimal survey design to detect as many planets as possible. So we start off with a model of our galaxy, and then we decide where to put our fields. In this case, I'm showing 7 different fields that we cycle through every 15 minutes. And so this is an image this is a dust map. So where it's dark, there's lots of dust, so you can't see through it. Where it's light, there's less dust. So we just image the sky in these 7 fields over and over again. We simulate stars in each one of these fields. And then we inject microlensing events into those stars. We see if we can recover those microlensing events, and then we inject planetary deviations and see if we can recover those planetary deviations, like you can see here. So this is a simulated detection of a planet that has a mass of roughly twice the mass of the moon, and showing exactly how we're going to detect planets with Roman. So the Roman survey of the galactic bulge, the center of our galaxy, is, again, 7 fields for about 2 square degrees. That's about 16 full moons, just for reference. It's going to be in the near infrared. Every 15 minutes, it's going to cycle through those 7 fields, exposed for a minute each time. And it'll do this on 6 seasons, each of which are 72 days. There's going to be a total of 41,000 exposures of this field for a total integration time of something like 432 days. This will be one of the longest exposures of the sky ever taken. So this just shows that simulated microlensing event again, with a simulated planet on top of it. This is for those of you for those technically minded of you, this is a 27 sigma detection. Typically 5 sigma is considered to be a significant detection. So this is very, very significant. This is a 23 sigma detection of a free-floating Mars mass planet. So we'll be able to see free-floating Mars mass planets relatively easily with this mission. So again, we can make some estimate of how common planets are and then ask how many of those we would detect. And the answer is we'll detect, maybe a few thousand microlensing planets using the Roman Space Telescope. And, I just want to warn you not to believe these numbers, because if we knew these answers, we wouldn't have to do the survey in the first place. So how is this? So back to our original goal is to, complete the census of planets. How is this complementary to the planets that we've detected so far? So the most capable exoplanet demographics mission was Kepler, which I think many of you are probably familiar with. It discovered thousands of exoplanets. And this plot is showing planet mass versus the separation in AU. So there's the Earth here. There's Venus, there's Mars, Mercury, Jupiter, Saturn, Uranus, Neptune. And so these red dots are all planets that Kepler discovered, and this red box here is where Kepler was sensitive to. So it was sensitive anywhere in here. Black dots are planets discovered by other methods, and these blue dots are simulated planets that would be discovered by Roman. And then this blue curve is Roman sensitivity. So you can see that Roman sensitivity is very complementary to that of Kepler. And together, they're basically sensitive to all planets with mass greater than that of the Earth at all separations, from 0 to infinity, including even free-floating planets. So this will be kind of the ultimate survey with which we can try to understand what planets are out there. This is how we find all the planets, and then use those planets to help us understand how planets form and evolve. Just to show you in the comparison to the other plot that I gave you, this is the sensitivity of Kepler again, and this is now the sensitivity of Roman. So it's very complementary and fills out that region of parameter space that was missed by the Kepler mission. Okay, so I mentioned that we can detect free-floating planets. Again, we don't know how common free-floating planets are. There's some initial hints that free-floating planets might be quite common, especially low-mass ones. If they are, Roman should detect a lot of them. And so depending on what you assume for the frequency of planets, free-floating planets, Roman will detect anywhere from a few hundred to a few thousand free-floating planets. And those planets are telling us something about how planets form, because those planets likely got ejected in the process of planet formation. We're also sensitive to potentially habitable planets. The sensitivity is not great, but we are sensitive to it. So we can actually see how common potentially habitable planets are. And we won't be able to actually look for life on those planets, but we'll be able to use that to inform other missions, which will be capable of looking for life on potentially habitable planets. I mentioned that we're sensitive to planets all the way down to roughly the mass of the moon. That means we're sensitive to moons orbiting giant planets. This is an example of a moon, simulated moon of 6 times the mass of the Mars, orbiting a Jupiter mass planet with a separation of roughly twice that of the Earth from the sun. And this is a very significant detection as well, 12 sigma. So we're sensitive to giant moons. This is a pretty particularly massive moon. We don't have moons like this in our solar system, but there's no real reason to think that they might not exist around other planets. But we're even sensitive to much lower mass moons than this, so that they don't make for quite as pretty pictures. So those are what we can expect from just microlensing. But actually, Roman, this survey is actually going to deliver a lot more science than that. And that's just because we're going to have so many data points and such a nice telescope and so many stars that we're just going to be able to do a ton of other science. So there'll be 100 million stars, as I mentioned, down to the sort of the kind of faintest things you can see in this image. There'll be tens of thousands of microlensing events. And with all that, we can actually do a ton of different kinds of science. And I won't go through all of this list, just to show you that there's a bunch of different science we can do, some of which has something to do with exoplanets, some of which is completely unrelated to exoplanets and is more about the how stars form and die and what the structure of our galaxy is. I want to focus though on another exoplanet application of Roman. So I mentioned transiting planets. So, transiting planets, you can detect planets that transit their host star when they pass in front, and the light from the star gets a little bit dimmer as the planet casts a shadow on its star. And those events are relatively rare because the planet has to be aligned very, very precisely along your line of sight. The orbit does. But if you have lots of stars, then you can detect lots of transits. And so this is two simulated transit detections of transiting planets with Roman. And you can see these signals are very easy to detect. And then again, we have hundreds of millions of stars with which we can look for planets around. And so that means by combining all of those different stars, we will be sensitive to and expect to detect roughly 100,000 transiting planets. Right. So this is a factor of 50 times more planets than we've discovered to date. And so this will obviously revolutionize our study of exoplanets. So we can put these transiting planets that we can discover with Roman with the microlensing planets and ask what regions of parameter space are we sensitive to. And so this shows simulated planets detected by the transit survey with Roman. The yellow here are simulated planets detected by microlensing. So there's hot planets, there's warm planets, there's cool planets, and then there's even cold free-floating planets, which are not shown here. And then the contours show roughly how many planets we'd expect to detect if every star has one. So for planets that have mass or radii greater than roughly that of the Earth, we'll be sensitive to all those planets with separations, again, from 0 all the way out to free-floating planets or to infinity. And that'll give us the ultimate data set with which we can use to find all the planets and understand planet formation. We'll be sensitive to the hot, the warm, the cold, and even the frigid free-floating planets with Roman. So this is just saying this another way. And we'll be sensitive to those planets in all areas of the galaxy. And so the three major components of our galaxy are the very center of the galactic bulge, the thin disk, which is where we live, and then a thicker disk, which is a little bit thicker than the disk we live in. Those are the three main components of our galaxy. We'll be able to complete the census of planets in all of those three major components and really use that to find all the planets. Okay, so now what? So Roman is being built as we speak. In fact, most of the pieces are already done. We're getting very close to the point where things are going to just start being assembled. So this just shows various pieces of equipment. There's the star tracker. There's the thing that's going to hold the instrument. There's the solar array. There's the high gain antenna. So Roman is going to send down about 1 terabyte a day of data, and so that requires a very high gain antenna system to transmit all that data. This just next video shows kind of where we are with the building and assembly of Roman. So this is the Goddard Space Flight Center in just down the road from me. This is the high base. So this is a clean room with a very tall ceiling. This is the instrument carrier, high gain antenna. Sunshade, solar array, shield. So if you are ever in the suburbs of DC and Greenbelt, Maryland specifically, and get a chance to take a tour of the Goddard Space Flight Center, I encourage you to do so. You can go and you can look at, well, at least now until they start until launch, you can go and you can see Roman being built, which it's quite impressive. So we are on track for an October 2026 launch date, which is exciting, but also very terrifying because there's a bunch of work that needs to be done between now and then. But not long after that, the data will start flowing. So Roman continues to stay on schedule and under budget, with launch currently anticipated in late 2026. That's great news, especially if any of you know any of the history of JWST. So that's just over 2 years from now. It's going to happen very soon. One very exciting thing about Roman is all the data will be publicly available as soon as possible after the observations are taken. So you can go and download the data from the MAST archive at Space Telescope Science Institute and analyze that data yourself if you would like to. And my team are busy trying to develop tools to allow as many people as possible to analyze that data, even if they don't have the full expertise of microlensing. Planet discovery should follow soon after launch, and there's going to be plenty of planets to go around. So those of you that might be interested in becoming astronomers or going to graduate school in astronomy, now is a great time to get involved. And you know, somewhere a few years into your graduate program or a year into your graduate program, the planets are going to start, data is going to start flowing, the planets will start being announced, and you could in fact be a part of that. So with that, I will end and say thank you and take questions.
Dr. Gaudi, first off, I'd just like to say thank you for contributing to our virtual speaker series in such a profound way. Everything that you've said has been incredibly impressive, and I know all of our MUAC members are very proud to have you participate in our series, so thank you.
You're welcome. Thank you.
At this time, we will take questions within our live chat for any of our concurrent viewers to ask questions of our speaker. Dr. Gaudi, while we're waiting, I do have a few questions for you, as well as I'm sure Dr. McBride does as well. So if that's okay, we'll go ahead and ask those.
Sure.
So during your talk, you did make mention about how thus far, most of the exoplanets discovered have been discovered by the Kepler satellite, if that's correct.
Yep.
Could you talk a bit more briefly on some atypical characteristics, possibly about some exoplanets that have been discovered thus far? Because I have read about some previously, and some things that I've read about has really fascinated me, and I'd like to see if you could touch on that a bit more.
So, are you interested in specifically some of the weirdest planets, or do you okay, sure. So, I helped to discover the hottest known exoplanet. It's called Kelt 9b. Kelt 9b orbits a star that's about 10,000 degrees Kelvin, so it's about 1.5 times hotter than the sun, and it has a period of 1.5 days around its parent star. The star is much hotter and more luminous, so it like blasts the planet with radiation, and the day side of the planet is actually hotter than most stars. So that's one example. We have planets that have periods around their parent star of only 6 hours. We have planets orbiting pulsars, dead stars. I don't know. What I like to say is that every rock you turn over, there's a planet there. So we found that like almost any kind of environment you can imagine, we found planets. So.
I think that is the coolest thing. Dr. McBride, do you happen to have any questions for our speaker?
So one question I have would be, if a student is interested in the work that you've presented here tonight, and maybe you can tell the answer from your own personal experiences, but what track would you suggest they go on? So somebody that's in maybe high school, or even somebody that's younger, what courses should they focus on to get onto a trajectory to study?
Yeah, so It's a good question. I think there's there's more than one path, and I think that should be be kept in mind. The traditional path is that you go to undergraduate and you get a degree in either physics or astronomy. Doesn't have to be those two, but those are the most common. You don't actually have to take any astronomy as an undergraduate in order to go to graduate school in astronomy. And there's a lot of people that don't. You learn the astronomy in graduate school. But then you go to graduate school in astronomy, then after that, there's lots of different avenues open into you. Uh, I think it's more common now these days for people to actually major in astronomy and as an undergraduate. That's what I did. There are quite a few programs out there that have majors in astronomy. And I will say that for those people that might be thinking they might be interested in astronomy, but are worried that, they might not be cut out to be astronomers, or they might change their mind and they're going to be left with a useless degree. I will tell you that the unemployment rate amongst people that have bachelors of science in astronomy is almost zero. And if you go on to graduate school, then lots of doors can open for you that have nothing to do with astronomy, like data analytics and things like that. So my joke is always, if this astronomy thing doesn't work out for me, I'm just going to go make a lot of money. I think that, there's if your people are passionate about it, if you're passionate about astronomy, even if you just want to go and learn about astronomy as an undergraduate, you're not necessarily sure you want to become a researcher or a faculty, or because the faculty life is not for everyone. I'm sure you agree with me on that one. Then there's lots of other things you can do from with a undergraduate major in physics and astronomy that can serve you quite well going forward. So.
All
Dr.
right, Hannah, do we have any in the YouTube?
Yes, we had a comment come in from Dr. Laura Stapleton. So she said, really interesting. She wants to know, is this the first time that this data that you've presented has been made publicly available?
So I actually didn't present any data. I presented some made-up data, but the data will be available after launch, and it'll be publicly available. Yeah. It'll be the first data of its kind, that's for sure.
So while we're waiting for a bit more people to send questions through the live chat if they have any, you did touch on largely about microlensing, and you explained how microlensing is sensitive to cool and cold planets, and it has a wide range of host masses. You even made mention of black holes. So could you expand a bit more on microlensing itself, maybe briefly, just for anybody that's maybe joining in at the current moment, to a takeaway message per se for microlensing?
Yeah. So the thing about microlensing that makes it very different than other techniques is that you don't require any light from the planet or the star that you're looking for the planet around. You're just using the mass of the planet and the mass of the star to detect the planet and star itself. And so that means that you're sensitive to things that are quite far away and therefore quite faint. You're sensitive to things that don't emit any light, like black holes, or emit very little light, like brown dwarfs, white dwarfs, or neutron stars. You're sensitive to planets around those as well. And so it makes it a very good tool to study planetary systems across a wide range of host star environments, or host environments, from brown dwarfs to stars to white dwarfs to neutron stars to black holes, all across our galaxy. So that's what makes it, I think, relatively unique. And that also presents some challenges. There's challenges with microlensing because it's a stochastic, low probability thing that happens. So you have to sort of move mountains to get enough microlensing events to find enough planets. But that's where Roman comes in and is so powerful, because it is exactly the tool you want to monitor all those stars to find all those planets with microlensing.
And then could you possibly reiterate one last time how many years in the making that Roman has been this large project for? Because you mentioned a possible launch date, I believe in October of 2026. So can you explain again how many years in the making this really has been?
Yeah, so I mean, it sort of depends on where you put the start date, but the official start of WFIRST was 2020, 2010. That was when it was recommended by the Decadal Survey. So if you go by that, it's been 16 years, and I've been working on it since then. But there were precursor proposals that weren't called WFIRST that, as I mentioned, fed into what would eventually become WFIRST, which would eventually become Roman, that were designed to do microlensing surveys for exoplanets and also dark energy and those kinds of things. And those had been studied for a decade before that, at least, sometimes in some cases even 15 years before that. So in some sense, this is a 25 or 30-year endeavor in the making. But for me personally, I started graduate school in 1995. And I started working on microlensing, and I worked on microlensing up most of my career. 2010, I got involved with, and I helped to develop microlensing as a way to find planets. 2010 is when it was recommended, and I've been working on WFIRST since then. So for me personally, this is kind of the culmination of my career to see this thing launched and see all this data come down. So it's quite exciting. So next 10 years of my life, 15 years of my life, the 5-year mission plus the 5-year extension, it's going to be spent with that. And then I feel like I can retire and be happy after that.
Well, I'd
Well,
just like to
fingers
reiterate.
crossed nothing happens on
Right.
the launch,
Yeah, exactly.
I'd just like to reiterate, you're such an impressive individual. Truthfully, we're so happy to have you here. We had an additional comment come in again from Dr. Laura Stapleton. She said, yes, I was referring to the data that will be made available after the launch. She said,
Oh,
that's so neat that we novices can analyze the data. Can you give us more details regarding the tools you're making?
yeah. So the tools we're developing are tools that will allow you to model the data itself in order to extract the parameters of the planets that are in that data, right? So you have it's like it's like anything else. You have data, you try to model it with a physical model, and then you use that model to infer something about the system that you're studying. So that model and the code, the computer code that fits that model is complicated, and you can develop it from scratch, but it takes you'd have to start from zero, and it would take a long time. And there's no real point in reinventing the wheel. We've been doing this for 20, 30 years now in microlensing. So we developed publicly available codes that you can download, and with a little bit of training and tutorials that are available, you can take those codes and apply it to actual data and extract the planets yourself. It's not like trivial, but it's a lot easier than if you had to write these models, these codes and models yourself. So, and our hope is to actually to set up some courses where we actually train people that have some background in physics and how to use these codes. So my dream is what I like to say is my dream is that some graduate student at some university that has nothing to do with me downloads this data, takes our tools, and finds the first planet with Roman. And that would be fantastic for me personally. I think that would be great. Or undergraduate, even. Why not?
Dr. Stapleton said, thank you. Very exciting. Um, so again, I don't see any more comments coming in through the live chat at this time. It's 7:03. Once more, I'm going to reiterate that we are so very happy to have you here. Everything that you spoke about this evening has truly, I think it's been an inspiration for myself, and I'm sure Dr. McBride as well, and all of our listeners, just to see everything that you've accomplished in astronomy and to see the time that you've put into this particular project. Me being a PhD student, not even pertaining to astronomy, it's truly inspiring, the dedication that you've had to this thing that you're so immensely passionate about. Your work ethic, it's really quite impressive. So thank you.
Thank you. Thank you for inviting me. This was a lot of fun.
Yes, definitely reiterate what Hannah said. Thank you for being the third speaker in the series here. It was great to have you. Please feel free to share the link for the talk. We're going to post that on our club channel, so that'll always be available. So don't hesitate to distribute that out and get some more views on that after we conclude tonight.
All right, great. And, feel free to put my email on there. People can reach out and send me email if they have questions. All right. Thanks, everyone.
Thank
All
you.
right, thank you.
Bye.